Great. So we'll go through this set of sections in the talk. I'll tell you about the origin story for IPC. We'll talk about Web3 in general, the scale that we need to reach, and how to cross the chasm. Then we'll talk a little bit about building the next generation platform, why we're building IPC, and how we aim to contribute to that. And then I'll want to walk you through how to think in subnets. I think this will be a useful exercise ahead of some of the talks after. So a little bit about the team behind IPC. So ProCollabs started with IPFS, and we built IPFS as one of the first projects. We've built a number of projects since. In 2014, we kicked off this open source thing. At the very beginning, it was pretty new and different, and so on. People didn't know quite what to think about it. There was a lot of excitement. It was definitely a visionary project. Fast forward to now, IPFS is widely used by a ton of participants. It's a huge building block for the entire industry. Lots of groups use it in core critical applications. A huge fraction of the crypto space uses it. Most dApps use it as a way to deliver their front ends. And so it has become like a very strong building block. In addition to the crypto space, there's a large community of participants around the world in all kinds of other mainstream applications that use IPFS for all kinds of things. And it's gotten to the scale of serving around 130 million requests per day, which is quite a hefty amount of traffic, and about 10 million weekly active users, at least in one of the gateways that we have visibility over. There's, of course, a ton of other gateways and a ton of other groups that we don't measure. The second kind of major project that I want to highlight is Lippy2P. It came out of a lot of our observations in IPFS. It came out of refining the networking stack through the years, and we wanted to create a building block that a lot of other groups could leverage and building their own systems. It leveraged all the lessons that we had learned through building IPFS and growing it, and gave that as a platform for a lot of other groups. Over time, Lippy2P has come to be adopted globally in the entire crypto industry. It now powers over 30 networks, at least, and including ETH2. It now secures around $300 billion worth of value, and it's the main networking layer that the industry uses. Then, of course, we built the Filecoin network. That's a major undertaking. It was an incentive structure coupling with IPFS. And over time now, that has grown to organize about 10 exabytes of capacity, which is an enormous amount of storage. And of that capacity is, the usage of that capacity is growing tremendously. We're about 1.5 exabytes of capacity used. Now, these numbers are enormous when you compare them to the rest of the blockchain industry. An exabyte is truly a gargantuan amount of storage. Most of the rest of Web3 in terms of usage in data is in the single petabytes. So you can think of maybe 10 to 15 petabytes as enough and sufficient to store most of the data in the rest of the networks. So over these three projects, we've gotten an enormous amount of visibility into how to build large-scale distributed systems, how to make them scale to reach these kinds of sizes, all of the serious challenges that are involved in building these kinds of things. And we've learned an enormous amount by building these. Now, we're taking a lot of the lessons that we've learned through building IPFS, Lippy2P, and Filecoin, and we're refining that into a new project called IPC. So let's talk about blockchains for a little bit. There's a whole bunch of problems with blockchains in general. The scaling, currently they're finally getting to scale to meet the demand, meaning a few years ago there was a lot of conversations about scaling. Most of the block space is completely taken up. Now with the rollups that are arriving, the blockchains are barely scaling to meet the demand that they currently have. That's not at all in line with the demand of Web2 applications. So when you think about normal Web2 applications and the scale of usage there, blockchains currently are not on a trajectory to scale to reach that level of demand. I'll talk a bit more about that scale in a moment. Also, blockchains have, in general, pretty bad composability. You can't easily call from one chain to another. There's a lot of bridges and a lot of tools and so on, but they're extremely complex to use. They're hard to reason about. Many of them are, if you don't get them right, then you don't secure the bridge correctly, and then all of the value that you're moving around falls apart. And so in general, it's difficult to treat the blockchain runtime as a whole across many chains as a good and safe developer platform that a lot of participants can build on. On top of that, there's really no good programmability across the space. You can't build a tool set that enables participants to grow a chain environment and scale it completely programmatically. Meaning, today when you set up a new chain or a new rollup or something like that, you have to do it by hand. A group of developers have to organize and kind of reason through that. That isn't an automatic set of operations that are just triggered automatically by on-chain smart contracts. Now compare this to the cloud, right, where you have complete automation of the entire set of systems. You can spin up VMs, you can spin up containers, you can reorganize the networks, and so on. Then on top of this, there's an enormous amount of complexity in putting all of these pieces together. When you are a developer team that is trying to build an application in the blockchain space, you have to learn an enormous amount of technologies and how to fit them together and the dangers of fitting them incorrectly. There's all kinds of things that you can do that can break the security guarantees across these. And so you end up in situations where your developer team has to become deep experts in several fields just to build a simple application. So this is very far away from a platform that the rest of the world can really use. So a lot of the work that has gone into IPC happened over many years. A lot of the first inspiration came in 2017 when we were working on the Falcon Consensus and Ivy Consensus, which is a whole other project I'm not going to talk about here. But that's where we started reasoning through needing things like partition tolerance, needing things like very fast block times, needing the ability to move extremely quickly inside of a single data center. And that's where we started thinking, what would blockchains have to look like in order to be able to scale? Then in 2021, we were pretty focused and busy building Filecoin at the time, and so we focused a lot of our attention on that. In 2021, we were finally able to return to these kinds of questions. We built Consensus Lab. A whole group came together to take on a bunch of these questions. You'll hear from a lot of the Consensus Lab team today. And we developed a lot of the tech that we now are putting into IPC. We also simultaneously built the FVM, and we did a bunch of R&D there to build a computing runtime with FVM that would be able to provide a good hypervisor for the entire rest of the industry. I'll describe a little bit more of what I mean by that. And now in 2023, we're productionizing IPC, bringing these set of technologies together, and you'll hear a lot about what it is and how it's going to work today. So if I kind of flash back to 2021, we kind of set these two goals to create kind of this hypervisor VM to be able to support all kinds of different runtimes and be able to call between them really seamlessly. And we painted this picture of trying to get to distributed runtimes that behave similar to things in the cloud and potentially very inspired by runtimes like the Erlang actor system, where you have very simple calling conventions between two different actors in this environment, and when entire sections of the environment can disappear and come back and self-heal. So over time, we've built these two sets of components. We've built the FVM. It's now live, powering the Falcon network. There's a set of runtimes that are coming to it over time. And we've built the IPC system. Cool. So let's now talk a little bit more about scaling and why this is such a big problem. So just kind of think outside of Web3 for a moment and think in the normal mainstream world. Think of your regular applications. Think of the cloud. Think of the scales of real-world applications. We're talking about massive scales of transactions. Just messaging is in the tens of millions of messages sent per minute, let alone per day or per week or something like that. We have hundreds of thousands of photos being posted, and those are now being taken with very high-powered cameras. You have lots of interactivity in social networks. As soon as somebody posts something, tens of other people will react to those things and create all kinds of additional messages. Think of email with hundreds of millions of messages sent per minute. An enormous amount of activity happens online all the time. In order for Web3 to succeed in its mission, to bake in a strong set of verifiability primitives across all of the internet, which is what Web3 is about, we're going to need to create a platform that can scale to this kind of operations. So today, the normal Web3 pathways are building very small set of transactional throughputs. We're talking about shooting for things like 10,000 transactions per second, 100,000 transactions per second. Maybe in some groups you hear 1 million transactions per second, and that is seen as a lot. But I want to tell you, like, that's just very, very far away from reality. We need to be shooting for billions or trillions of transactions per second in order to hit the level of scalability that the broader web requires. And so in my perspective, after being in the industry now for about 10 years, is that this scalability is what we need in order to bring Web3 to mainstream adoption. We need to be able to build consumer applications, consumer-grade applications with high-quality UX, and be able to onboard billions of people onto them. In order to get there, we need to make it easy to build these kinds of things. Easy means that the platform needs to scale to these sizes. Easy also means that developers need to not become experts in every single deep technology field involved in the platform. When you develop an app today, you don't have to become in the normal cloud. You don't have to become an expert in distributed systems or networking or virtualization and operating systems, or you don't have to reason through how the cloud is architected in order to build and deploy your application and scale it to billions of users. So now, the IPC in general is very inspired by the architecture of the internet. We want to build a protocol that falls in line with the rest of the IETF protocols in terms of its ability to operate in the network and be partition resistant, partition tolerant, and be able to lean on subnets to be able to go extremely quickly in regions of the internet. Meaning, if you have a lot of participants in a region of the world, they should be able to interact with each other and transact with each other at really fast speeds without having to go all the way around the world to some other place. I will talk about more about that in a moment. To go back to the scales for a moment, if you think about storage sizes for most of storage networks or things like that, we're talking about exabytes to zettabytes, 10 to the 15 or 10 to the 18 objects across all web applications. Typical databases have tens of thousands of transactions per node, and you have a good scalability where as you add more nodes, you horizontally scale. Even Amazon Lambda on its own has on the order of tens of billions of transactions per second. So this is what we're shooting for, and the Web3 space is far away from it. And even thinking about Filecoin specifically, as a lot of us work on the Filecoin project and the Filecoin network, when we think about the scale that we want Filecoin to achieve, we're thinking of truly massive scale amounts of storage, massive scale number of requests per day, massive scale numbers of objects. And so we want to be able to support the storage of the world, and in order to do that, we need this kind of scalability. So really, we're shooting for this kind of target, right? So if you think of these axes as the broader scalability of technologies and the broader security, so it's great that that you have really high security in the consensus, in the protocols, in blockchains, but we really need to be able to vault over to hit this area of the space where we get that level of security, but we have the scalability of the cloud. And just most next generation chains are just very, very far away from this. So we need to do something that leapfrogs all the way there. Great, so we talked about broader scaling. We need to be able to build a technology that can scale to that level. Now I want to talk about how we're gonna do that. So what you're gonna hear about today, the tech that you're gonna hear about today is a combination of three main components. The IPC scalability protocol that combines a whole set of chains in a recursive tree structure, the FVM, and this broad effort around delivering high-quality developer experience. So the DX part is not a specific piece of software. It's rather an enormous amount of effort to get to extremely high-quality developer experiences. Great. So this is the slide that I had to skip. We have here again. I'll go through these properties as things that we're solving for. So we want to be able to hit internet scale. That's one of the major thrusts and the major focuses of the whole project. We want to be able to have fast local finality. What we mean by that is that we need a consensus protocol that can give us within data center finality for a lot of transactions. That means that the consensus needs to confirm without having to go to the rest of the world. It needs to confirm in data center latencies. That means single milliseconds or 10 milliseconds. We also would like to have things like secure global finality in the style of normal blockchains. So we need some kind of checkpointing structure, meaning you need to have a local consensus at a data center level and then be able to bring things up into the global consensus. We need things to be market tunable, meaning that different applications are going to require different characteristics about their networks. They might require different validator sets. They might require different connectivity to the rest of the network. They might require privacy. So there are many groups building blockchain applications that would like their subnets to be private and prevent certain parties from adding certain contracts or prevent parties from even observing what's going on. However, those private subnets need to be able to interact and transact with the rest of the world. We also need to be able to be partition tolerant. So this is a key property for all internet protocols. If your internet protocol does not work with a big network partition, it's not truly an internet protocol. It's a good protocol for a set of applications, but it's not going to work for robust applications that are mission critical. Mission critical applications are things like just text messaging, things like emergency services, things like calling, anything that you need in any kind of moment of crisis or any kind of moment where the normal situation has been upset in some way. You need the base layer platform to support those kinds of systems. And today, blockchains do not do that because you have to connect to the global consensus. So if your region, for whatever reason, disconnects from the rest of the internet, you lose all transaction capability sets. And that's not a good position to be in. We also need to be in a position where we can encrypt all transactions before they're committed so that you completely circumvent all this MEV set of problems, and you avoid censorship in that layer. So a lot of problems go away if you encrypt transactions first, you commit them into the network, then you reveal them and process them. Now, the next thing I want to talk about is a thing we call the interplanetary principle, and this dropped out of IPFS. So when we were designing IPFS, we had this really good mental exercise. Just think of a protocol working across Earth and Mars. That really helps humans think about the latencies involved of two devices communicating. If your protocol feels wrong when you're designing it at those scales, then it's going to be wrong for data centers and mobile phones to communicate to each other. What do I mean by that? So if you design a protocol that requires multiple round trips over this very long delay, then when you move it into the normal phone or browser or cloud environment, those delays between your phone and the servers, while not perceptible to you, are enormous compared to the delays locally happening within your computer or the delays happening within a server. So this interplanetary principle of forcing ourselves to design protocols that work across these vast distances to minimize the times that you have to jump through this terrible latency tends to yield much better protocols. The way we sort of think about it is, you want to design distributed applications with tolerance for interplanetary delays. If your protocol does that well at all scales, then it'll work really well for servers and Earth. Meaning, it'll help you arrive at a much better architecture that works correctly for computers here on Earth. And this is a foundational thing with IPC. We're designing the entire thing so that it works, so that it's a sane protocol to run within a data center operating transactions there, or within a city on operating transactions there. So let's talk a little bit about why we have a tree structure and so on. So imagine that each one of these circles is a single blockchain. So it's not a single node, it's an entire consensus protocol running. And of course, now the rest of the blockchain space is now adding rollups and L2s and so on. So we now, of course, have the second layer. Now in computer science, whenever you encounter this kind of problem, The good thing to do is just make it recursive. Build a system that is completely recursive all the way, where you can go to arbitrary depths and keep adding layers to the tree as you need them. You want a system that doesn't treat the top as a special privileged spot. You want to be able to move down as far as you need. Think of it kind of like a file system or the web with different levels of hierarchy, or DNS with different levels of hierarchy. You want to create a protocol that can do this. So in IPC, what we do is we have a structure and a framework for being able to create subnets and anchor the security of that subnet into the parent and lean on the parent to do cross-chain message passing. So we do a lot of the cross-chain invocation. We solve a lot of the cross-chain invocation problems by leaning on the parent to be able to route the messages. Now that's a little bit slow if you want to go from deep in the tree all the way to some other part of the network. That can take a long time, so you can run other protocols to make that transaction faster. But you can always fall back to the security level of going all the way back up and all the way back down the tree. That kind of structure gives you a very stable foundation on which to build pretty successful applications. Now, a really neat property here is that when we're building each one of these circles, it's not a roll-up. It's a full chain. So it has data availability baked in. It has data explorers baked in. It has the ability to partition from the rest of the network for a period of time and then come back. So you can take an entire subtree, disconnect it from the rest of the world for a while, and then bring it back and resume. And one of the key things is you can establish required properties to join a particular subnet. So a creator of a subnet can define, oh, they want a certain set of latencies to be required in order to be able to participate as a validator. This is what gives you the ability to localize a consensus network within a specific data center or a specific city or something like that. Cool. So another way of looking at it is kind of like this. You can see sort of the tree on one side. You can see the chains being built. The lines here are kind of checkpoints between the networks. So with this kind of structure, you get an environment that gives you this flexible runtime that can give you arbitrary levels of child subnets. The subtrees can be available through partitions. It can be regionally constrained. And you have both horizontal scaling to being able to add sibling subnets, or vertical scaling where you can keep fanning out. If that chain is suddenly congested, you can keep breaking down into lower and lower levels. Now, one of the key things here is that we make cross-chain calling across all of this very transparent and very seamless to use. So in our perspective, we think of the world of blockchains as having thousands or tens of thousands and potentially millions of chains that you have to reason through. So you need the platform and the software to abstract all of that away for developers. It needs to be seamless to be able to call from one contract to another contract in some other chain anywhere else. And we need to get to a platform that can give us that. And the whole industry is kind of fairly far away from getting there. Cool. So I'll mention. Yeah, there's a whole set of things that drop out of having subnets. You can get to scaling a single application with a bunch of subnets. So you can think of that tree as you can have one application mapped to that tree. You can scale a whole ecosystem, meaning you can create a tree of subnets for a whole thing. We're thinking about this with the Falcon network, where the Falcon network might get a whole set of regions that are localized in certain environments. So many different applications can leverage those regions. You can think of application-specific networks. So you can deploy a blockchain that inhibits any random contract being added. It just carries the contracts that you need for that specific application. And so think of it as the way that you would think about deploying a VM today. If you spin up a VM or a container in an operating system in the cloud somewhere, you pick what programs are going to go in there, and you don't allow random users to inject random programs into that computer. You're picking, as a developer, what exactly is going to run. This lets you use the smart contract environment to write much more sophisticated and larger scale applications. You no longer have to write small business logic that is going to be heavily congested with a ton of other applications. You can actually start putting larger and larger programs in there because you have the benefits of the scalability and the ability of constraining what's going to run there. And of course, you can use the different kinds of validation structures. You can do things like optimistic compute networks. You can use hard verifiability. You can use ZK to verify and validate the aggregation of a subnet. You can do optimistic checking and so on. All of those need to become configurable parameters as you're generating these subnets. One of the things that we're shooting for in the long term is to be able to get to hard privacy, meaning a subnet could be in full FHE. That means you have a fully homomorphically encrypted subnet running a set of operations in the network. Now, of course, that's maybe 5 years away or something like that. I'll touch on FVM a little bit. So switching gears for a moment, this is not a full FVM talk, so I won't talk about it a lot, but just to give you a bit of a mental model. We designed FVM thinking about the traditional cloud and the hypervisor nature of the computing environment there. You want to create an environment that makes it easy to bring whatever programs you have into the blockchain space. You want to create a layer that enables all participants to interact. You want to get away from fragmentation in ecosystems. So we want to create an environment where any different VM runtime that you have across the blockchain space or outside of the blockchain space could be brought into and run within FVM. And so we take as inspiration the traditional OS virtualization layers or the traditional large-scale compute environments like Borg or Kubernetes and so on. And then we think about how new technologies like zero knowledge or FHE can be used to do some of the computation in a well-scoped way. And so we think of FVM as this hypervisor runtime that can support lots of different VMs on top. And of course, not just smart contract VMs, but you could think of, because it's running in WASM, it can support many other kinds of things. So imagine getting to a point where you could have a subnet in IPC running a Python interpreter or something like that. That's when you can start doing machine learning within these things, and it gets pretty interesting. A lot of the rest of the team is going to talk about the developer experience, so I'm not going to dive too deep into that here, but just know that a big focus for the whole team going forward is to create a very seamless developer experience, and we want to create an environment that is inspired by the best of the best in the mainstream world, and we want to bring that culture into the Web3 space. There's an enormous amount of work here, so I'm not promising that we're there today. There's an enormous amount of work that we need to do as a whole community to get to that. Great, so I want to finish by walking us through how to think about subnets. So let's take one simple version. Let's think about compute pipelines on lambdas. How would we do that in IPC? So the way to think about it is like if you want to build some large-scale distributed system to process a lot of compute jobs in some compute pipeline, think of like millions of jobs per hour or something like that. The way that you want to get into that, and I'm going to just broadly sketch the design. Of course, you'll hear some talks later that will go in depth at how some of these works. I just want to give you the mental intuition. You want to do things like first, you can use CIDs to point to the code and the data, and so that means you can bring all of those assets into IPC because FVM is IPLD compatible and so on. So you're able to deal with the CIDs directly. You can of course store those on Filecoin or store them somewhere else, but bring them into the environment. You compile whatever programs you want to run in this compute network to WASM so that you can run them on FVM. You can then use IPC to create a tree of chains, and you want to size the tree appropriately to what scale you want to be able to run. So with this kind of scale, you would want to fan out to maybe 3 layers or something like that. And then you need a scheduler that is able to select where to place each job. So there might be different considerations there. You might want to build a network that moves the computation to where the data is, so your scheduling is going to have to be aware of what data lives in what set of machines so that you can move the computation there. Or you might have jobs that are not data intensive, where they're really just, you don't care about where they run, just you want them to run as fast as possible. So a scheduler like that would be more about integrating information of what nodes are congested or not, and where to send the computation. And you would just think of most of the hierarchy as coordination. like the inner layers of the tree would be about coordinating the subnets, and you would place all the compute jobs just in the leaves of the bottom of the tree, and you would just run the computation there. In the leaves of the tree, you don't need many nodes in each one of those subnets. You don't need like thousands of nodes there. You could have a few nodes as long as they're checkpointing everything to the parent and you have verifiability. You can rest secure in the structure. Now let's think about a social network as an example. So same kind of similar sort of story. Think of a use case where you're building a basic social network for billions of users with a bunch of posts, direct messages, all of this kind of stuff. Same sort of sketch. You assemble a tree of chains to store to manage all of the transactions. In this setting, you might want to create automatic scaling for the tree to grow with the demand. Social networks can spike really quickly, so you want to be able to grow the topology to be able to deal with the demand over time. You want to assign specific users to specific subnets, for example, and process their transactions there. So whenever you post, your client would first connect to the root net to figure out where to go. It would then connect to whatever network you're supposed to be posting in, and it would distribute your post there. Then, of course, separately, you can have read replicas somewhere that are indexing the information and displaying it to parties. And you could, in this setting, store all of the information about the social network directly on chain. You can put all of the accounts, all of the posts, all of the DMs, all of the reactions, all of that can just go in the state tree. And that sounds like crazy in Web3 land, right? But because we have this recursive scalability, we're not worried about block space, and we're not worried about the state growth in the tree. If it gets too big, just you split down and you fan out and you keep doing this. You could even add media into the state tree. You could imagine adding pictures or images and so on. And then over time, if they're big, you can then bring them into Filecoin or something like that. Now, let's think about games for a moment, and we're going to go through 3 examples here. So let's think of just simple board games for a moment. These are, think of easy turn-based types of things. A lot of people have built these already in blockchains. However, there aren't many of them because it's still pretty expensive to run these on chain. And there's actually a lot of things that go into building a board game, like you need a chat stream, you need like accounts, you need to track scores. All of this you need a lobby of like matchmaking to pick who's going to talk to who. All of that sort of stuff ends up being other programs that then people today put in separate servers somewhere else. So it'd be great to just be able to bundle all of this directly into the same place. So with IPC, you can create, again, a tree of subnets. You can put accounts and the persistent leaderboards and all of those kinds of things in the higher subnets where you route the information. That data is very small, so you can just put it there. Then you use a set of subnets to run the games. And you have a lot of different strategies here. You could just create a topology and then route games to multi-home several games in each subnet and kind of reason about the congestion. You could also spawn subnets programmatically. Because subnets are cheap, you could just spawn a subnet per game. That's not crazy expensive. You could do something like that. And of course, you can store all the game artifacts, code, static assets, et cetera, as CIDs on IPFS or Filecoin. Or in some cases, if they're small enough, you can just dump them directly into the state tree. Now, cool thing here is you can even use IPC to store the chat going on in the game. You can write the chat stream directly into the subnet and use that as a venue. So as a client, you're just connecting to one environment and using it to distribute all of the information. Now, when you think about imagine the game starts, you go into a subnet, you have your chess game, you chat, hopefully you win. At the end, what you really want to report and bring back to the rest of the chain, A, is verifiability that was computed correctly so that there's no cheating in the games and so on. And B, you really just want to aggregate the winning scores and so on, so you don't need to bring all of the rest of the data. If you wanted to preserve it for long-term archival, you can then dump it on Filecoin, or you can keep that subnet around, or you can garbage collect it. This sort of depends on what user experience you want to go for. So let's do something even crazier. Imagine an FPS, right? What? An FPS on a blockchain? That's crazy. So for those of us that have played a lot of FPSs or think about how they're built and so on, you need a really fast tick time, right? So you want something I think 66 ticks is when I've thought about these kinds of things. Maybe this is higher now, I don't know. Maybe this is like pretty good for human perception, and we're probably not going to get faster. But this really means around kind of like 15 milliseconds for like you sending your update on the server, sending some information somewhere else. So you as a player and your client is broadcasting updates really fast. The server is aggregating all of these, computing what is supposed to happen, and then broadcasting it out to everybody really quickly. So that sounds like it doesn't fit blockchains at all, right? However, with IPC, you can construct this kind of thing. And this is a demo that we're going to go for. Like we don't have an FPS on blockchains yet, but I promise that we'll get there. Someday we'll be able to demo a full FPS running on a chain, and that'll be really awesome. What you want to do here is you want to create a tree of subnets. You can put all of the normal game accounting information like the accounts and lobbies and so on in the higher layers of the tree. And then you can spawn an entire subnet per instance. Now the neat thing here is you can configure that subnet to behave differently. You don't have to use the normal consensus protocols for other blockchains. You can use a specialized consensus protocol for that specific application. So you can change how that works, meaning you can turn that subnet to behave like a normal game server. That can now behave like a game server, collecting updates from parties, committing them very quickly, and then spreading out all of the operations to the users and hit the normal requirements from normal games. Now again, you can store all the game artifacts, code, static assets, and so on as CIDs. They're native in FEM, and so on. Now the kind of even cooler stuff, like FPS are nice, right? But what about MMOs? Let's shoot for really awesome games. This is a setting that even lends itself very well to this sort of setting, right? You can use again IPC to assemble a tree of chains. You can think of each region as a different subnet. You can have a topology where if you need other services, you can create different subnets to run some of the programs that you need to run to maintain the world. And then you can lean here on a couple different approaches. You could have sort of a batched approach where you commit a lot of the operations batched, or you could, again, follow the kind of FPS route of really making it operate like a game server. You could, of course, couple IPC to other software. You could have a normal game server running on the side, running all the optimistic computations. You compute the resulting state, and then you batch update that into the subnet, and then from there on to the rest of the world. We're building IPC so that it's a very modular sort of thing and configurable, so you can tune it however you want for your application. Now, in this sort of setting, you would put all the objects and players in a particular region into a subnet leaf. You would kind of interact there. You could probably put markets and other really more sensitive stuff higher in the layers that are more secure. Think of the leaves at the bottom as being inherently less secure than the things in the top. You have to wait for a period of time until that security syncs. And then, of course, if a user moves from one region to another, they would leave that subnet and enter another. Cool. So hopefully this was useful to help you think about how IPC, how to think in subnets, and why we're building IPC. And I will hand it off to the rest of the team. Thank you.